Hey everyone, and welcome to episode 11 of Q for Problems. This is part 2, so just continuing on, here's the problem that we were trying to solve. So it was problem 11 of Project Euler problem set, and in the first part 1, we looked at solution 1. So that solution basically involved joining on a column of zeros onto either the left or the right hand side, and that would account for the overlap of when we generated the index to index into the list. However, in this solution 2 that we'll look at now, we're going to instead just try to outright create the correct index that doesn't have any overlap without having to join on this extra column of zeros. So let's have a look. Looking here at an alternate approach for solution 2. So we're going to just simply have, we're not going to be adding on this extra column, so our row count and column count will be the same, and it will just be a count of n. And then our striated index, or I, that we'll be scaling for each direction is just going to be an index of essentially the first horizontal, and then we will scale that according to the direction. And we can create an index of the rows or columns. We'll just call it Ri. So here R is the count or the number of columns or rows, but here I've just chose R just instead of C. We then need to scale each of these row indexes. So we can just multiply that by the number of rows there are. So you can see that gives me 0, 5, 10, 15, 20. So why do we scale by that amount? Well, if I create quickly a matrix of the indexes of our matrix of our original matrix, so you'll see what I mean. If I run that, you can see that this is just basically the position of each of the indexes. You can see here that the first row, okay, so that is the one that we have here essentially. And then the second one is basically the first one add 5. The third one is the first one add 10, and so on. So that is where the scaling comes from. So we can create a variable idx to hold all our indexes that we're going to use. And our horizontal is I plus each of these scaled values. So r times ri, and there that is the horizontal indexes. For the vertical, we do a similar thing. However, we need to essentially pre-scale our I value. So we multiply I by the number of, essentially it's the number of columns there are for the verticals, but columns and rows are the same. So here we have our base I, and then to this then we just need to add our Ri, the scaling for each row then in that case. So if we do plus Ri, run plus, right, you can see here the first one. So if I maybe just show the first, or maybe we'll just do the first. You can see this will correspond to the very first column. So 0, 5, 10 is, if we look here, here's our index matrix. That would be the first 3 items. And then the next one is going to be the next 3 items. And then the one after that will be the last 3 items. And then that repeats then over all of these. So that's what each row is then. That is basically each row here is the vertical. So row 1 corresponds to column 1 here. Row 2 corresponds to column 2. So that is our vertical. So I can just do idx and then join and look at that. So that is vertical and horizontal now joined together into idx. So the next thing then to do is essentially the diagonals. So we can calculate how many possible times we're going to have to move vertically. So essentially when we move through this, we do the diagonal, say we're doing the 3, we do these 3, and then we would go over the row, and then onto the next one we would do this, this, and this, and then we would move on to the next one, do this, this, and this, and then once we move on we can't go any further because there's not enough elements. So the number of possible vertical moves is given by 1 plus r minus x, so 3. So there you can see that if I run our I must have deleted it, so if I just get that back, our 5 tick till 5 times 5, just to get our space in there, just to get our index back. You can see that we're going to be able to move down to the third row. Before then, on the fourth row, we would have no more room to actually do the diagonals anymore. So that gives us that. And then our starting index is going to be r times till, and then that how many vertical moves we can make. So if I run that, this basically tells me the starting index on each of the rows. So again, if I look at this, you can see whenever we're doing the right diagonal, I moving left to right, the starting index is going to be this. Then on the next one, on the next time, it's going to be 5, and then the next time it's going to be this, and then we move across. So that is our starting indexes. And then we also just need to create this index of the number of actual items we want. So we're going to use this then to scale per item, because remember the diagonal has like a staggered form of scaling. So remember the first item doesn't move at all, and the second one is actually the horizontal move down one row, and then the third one is actually the horizontal move down 2 rows. So this basically creates that staggering. And then we can work out our first row diagonals by doing I plus r times xi. So you can see that this is going to be the diagonals for the very first row. So 0, 6, 12, and then 1, 7, 13, and then 2, 8, and 14. So that is one row. So then to actually scale that, to do it for each, we have to move down to the next. They start from here and then move down again. They start from here. We can just add onto D. So if I do plus and then each right to D, then you can see, so the first row is this part here, what we had, then the second row then, so you can starts at 5, and then the third row then starts at 10. So that's the 3 diagonal for each of the 3 possible rows that we can do a diagonal for. So that actually is our right diagonal index. So we can do, again, IDX join that. And then the final one then is to do the left diagonal. So the left diagonal, again, we just have to kind of alter the scaling factor. So our starting index essentially will be 2. So again, if I look at this, remember that where are we going to actually start? It's going to be from here, because the left diagonal needs to move this way. So it needs to, which one do you actually have to start from? So it's going to be here, and then move on to this, and then move to this as its starting point. Then how do we know which number we move on to next? So it's going to be r minus 1. So the reason is, so if we start in here, 1, 2, and then 3, and then 4, we have to move 4 numbers to get to the next value in that diagonal. Similarly, then 1, 2, 3, 4 to get onto the next value of that diagonal. So that is the move. However, when we actually working with indexes, so we need to minus 2 as well, because indexing starts at 0. So we actually want to use this as an index value rather than just an actual normal value. So from that, then we can do xi times by r minus 2. So that gives us that scaling on how much we have to move, and then scales it by, remember, our xi is our index scale for each of the steps that we need to take. And then we need to also add x minus 1 onto this. So if I run that, you can see that gives me 258, and then all we need to do is actually add that onto I, because remember, I needs to be scaled by that. And that gives us our first row diagonal. So again, if I look at our values here, we can see that the first column is 2, 6, 10. Second one is 3, 7, 11. So 3, 7, 11. And then 4, 8, 12. 4, 8, 12. And then we need to just do that then for the other rows as well. Again, that just means adding on this, or add each right of D. And then that gives us our 3 rows like we had before. And simply we can just join that to our IDX. So now we've got all the directions done, we can basically just do raise on n. So remember this, we're using a flattened version of n here. So if I do that, that gives me all the values. And we also then need to do PRD each. So each row here, if I just do first, remember, is itself a list of lists. So whenever I do prod, it's going to do on each of these rows. And then because, say, this is the first row, it's actually going to do a column wise on this then. So if I take that away, that gives me all my products. So you can see each row is actually 3 groups of numbers. So whenever I actually do the prod each on this, that gives me still this. So I need to flatten this and then just do the max. So I just do raise on that to get the flat list, and then max to get the final result. And that is essentially the full solution built out. So now I'll just copy in the actual as a function. Um, so it will look something like this. So if I run that, and then again, if I pull in the actual problem and set x equals to 4, and then run s2 on n x, you can see that gives us the answer. For the performance test, I'm going to first compare the actual problem. So we have that loaded into n, and x is 4. And so here we run the test 10,000 times for each S1 and S2. So if I run that, you can actually see that S1 in terms of time is actually better by a factor of 2, where there's only a slight memory improvement of S2 over S1. So for the actual problem in question, S1 is the more efficient solution. However, if I here generate a matrix, so a 10 by 10 matrix, a 100 by 100 matrix, and a 1000 by 1000 matrix, so I have already pre-run this because it does take a few seconds to run. And so I run the test then where I select 4 adjacent elements and 8 adjacent elements for each of these matrices, and do this 100 times. Um, then we can have a look at some of the results. So first of all, where the 10 by 10 matrix, and as you can see here, this is the 4 and the 8 for S1, and then the 4 and the 8 for S2. So S1, again, shows a very slight improvement over S2 for the 10 by 10 matrix. If we look at the 100 by 100 matrix, again, S1 has a slight improvement in terms of time over S2 for both the 4 and the 8. However, when we move on to 1000 times 1000 matrix, which would basically be a matrix of 1 million elements, we can actually see that S2 has a much improved time. So here it's by a factor of just over 2 as well. And if we increase the size even more, again, you would have a bigger improvement. So S1 seems to be the more efficient solution for smaller matrices. However, S2 seems to improve whenever the matrix gets up to the 1 millionth element size and beyond. And we can also see here that whenever you have 4 adjacent elements compared with 8, that the 8 takes almost twice as long for, say, S2, and even in the case of S1. So the number of adjacent elements you are actually taking will affect the result as well. But yeah, that is everything for the performance. So, just a little side note, we have done all the Project Euler questions apart from Project Euler number 10 up until this point. So, we skipped number 10 and the last episode because problem 10 simply just wants to find the sum of all the primes below 2 million. And we already have discussed in episode 3, so go check that out. If how to generate primes up until some number. So it's not using anything new. So I just wanted to include the solution here just for completeness. So essentially, we just generate the primes up until 2 million and then do the sum of that. And if I run that, this is the answer. Yeah, that is everything. Thanks for watching. Share your solutions and comments below, and I will see you in the next episode.